And welcome back to our SPI Doppler Review series. This is the clinical application section. Thank you for making it this far. So now that we've worked through fluid principles, flow patterns, hemodynamic equations, Doppler physics, signal processing, and instrumentation, now we're ready to bring everything together. So in this episode, the last episode, we're going to focus on phase 7 clinical applications where theory becomes practice. We're going to apply Doppler principles to real diagnostic scenarios. We're going to interpret waveforms, recognizing abnormal flow patterns, and understanding how system settings impact clinical accuracy. So understanding clinical application is essential because, again, the SPI doesn't just test definitions, it tests your ability to think through scenarios. So when you can connect physics interpretation and waveform interpretation to patient care, the exam questions become integrated rather than isolated. So let's go ahead and move from understanding how Doppler works to understanding how Doppler is used in real world imaging. Again, this is our section slide, our recap. So now that we've worked through instrumentation, again, we took a step back, we looked at the full progression of phases. So let's do this all over again. All right, so we began with fluid basics, building an understanding of what blood is and what allows it to move. Then we explored flow types. We were identifying the different velocity patterns within a vessel. After that, we moved into the hemodynamics, where physics explained those patterns mathematically, connecting pressure, resistance, radius, and flow. Then next came Doppler fundamentals, where motion became frequency shift to the Doppler effect and the Doppler equation. Then we examined signal processing, where those frequency shifts were converted into spectral waveforms. And then after that, we covered instrumentation, learning how the system controls, like the PRF, the wall filters, the sample volume, and the angle correction influence what we detect and measure. So today, we transition into clinical application. So if the previous phases built the science and mechanics of Doppler, clinical application brings it all together. This is where you interpret waveforms, you recognize abnormal flow patterns, apply correct angle technique, and understand how system settings affect diagnostic accuracy. So each phase has built logically on the one right before it. And so right now we're moving from understanding how Doppler works to understanding how Doppler is used in real patient care. All right, so we're almost there. So again, in this final phase, we're going to bring everything together by examining Doppler modalities and how they're applied clinically. We're going to begin by identifying which Doppler display is not angle dependent and why that matters in certain imaging situations. And then we're going to clarify which modality cannot determine flow direction and what that limitation means in practice. We're going to discuss which technique is best for detecting slow flow in deep vessels. This is a concept frequently tested on the SPI exam. And from there, we're going to examine variance color maps and how changes in the hue reflect turbulence or disturbed flow. And then we're going to review the advantage of spectral analysis, particularly its ability to display peak systolic velocities and provide quantitative velocity information. So the section focuses on selecting the correct Doppler modality for the clinical situation and understanding not just how Doppler works, but which tool is most appropriate for the question that's going to be asked. So let's get started with the first question in this section. So the first question is, the angle of incidence is not important with which Doppler display? And so the answers to choose from are A, color, B, power, C, duplex, or D, spectral. So the correct answer here is power. So with power Doppler, the angle of incidence is not important, and here's why. The power Doppler displays the amplitude or the strength of the Doppler signal, not the frequency shift. So it shows presence of flow, relative volume of moving blood, but it doesn't calculate velocity, since velocity calculations depend on that cosine theta. And power Doppler doesn't calculate velocity. Angle doesn't matter in this case. So let's look at the other answers and why they're not correct, incorrect, or not the best answer. So A says color. Color Doppler displays direction and mean velocity. So velocity depends on angle here. So color Doppler is angle dependent. Answer C is duplex. And duplex, remember, is it's in the name. It is the two modes, the B mode and the pulse Doppler. So remember that they're sharing the array there. So the pulse Doppler calculates velocity, and then velocity depends on angle with this one. So duplex is also angle dependent. Um, D was spectral, and so spectral Doppler just measures the peak systolic velocity, end diastolic velocity, and flow direction. So all of these require angle correction. So again, spectral Doppler is definitely angle dependent. So if the display measures velocity, that's angle, the angle matters in that case. If it displays a signal strength only, angle doesn't matter. So remember that power Doppler equals amplitude display, so no angle dependence is required. Okay, let's go to the next question, and it's asked, which of the following Doppler displays cannot determine flow direction? And again, the answers available are A, color, B, power, C, spectrum, or D, continuous wave. And again, the correct answer, unfortunately, it's highlighted there, is power. So power Doppler cannot determine flow direction. And why is that? Power Doppler displays the amplitude, remember, the strength of the Doppler signal, the presence and the amount of moving blood, but it doesn't analyze frequency shift direction. It doesn't care whether flow is toward or away, and it only shows how strong the signal is. That's why power Doppler is often a single color, usually orange or yellow. But let's look at the other answers and determine what's wrong with those. So again, A, the choice was color. Color Doppler absolutely determines direction. So red is something moving toward, usually, and blue is something moving away, usually. And direction is one of its main functions. Answer C, and so that was incorrect. Answer C is spectrum, and so spectrum Doppler shows direction using above baseline, so that means something's toward, or below baseline, and that means something's away. So again, this one clearly determines direction. And D, continuous wave. So CW Doppler, continuous wave Doppler, still shows positive versus negative shifts, above versus below baseline. So it also determines direction. It just can't determine depth. So if the mode displays velocity, it can show direction. If it displays amplitude only, then it cannot. So power Doppler equals amplitude display, no direction. So hello everybody, that's me down there in the little tiny cameo there. I had to make it smaller and move it to the bottom, even a different shape. All right, let's move into the next question. And it says, which of the following pulse Doppler techniques is the most likely to demonstrate slow flow velocities in deep vessels? Answer A is color Doppler, B is duplex imaging, C is power Doppler, and D is spectral analysis. And so you can see the answer being highlighted there. I'm sorry I couldn't remove the highlight on these images. It's power Doppler. Power Doppler is the most likely to demonstrate slow flow velocities within deep vessels, and that's because power Doppler displays the amplitude, again, the strength of the Doppler signal, not the mean frequency shifts. So it's more sensitive to low flow, less angle dependent. It's better at detecting weak signals, and it's less affected by aliasing. So in deep vessels, signals are already weakened due to attenuation. Slow flow produces small frequency shifts, so power Doppler doesn't rely on velocity magnitude. It just looks at signal strength. So this makes it ideal for slow flow, deep vessel, and small vessel. Now let's look at the other answers and look at what's odd or wrong about those. A says color Doppler. So remember, color Doppler estimates mean velocity using frequency shifts. So slow flow produces very small shifts that may not be displayed well. So it's less sensitive than power Doppler for slow flow. B says the answer is duplex imaging. So just remember, duplex just means B mode and spectral Doppler. So it doesn't improve slow flow sensitivity. Spectral Doppler can actually miss very low flow signals. And then D, spectral analysis. And so spectral Doppler is excellent for velocity measurement, and it's not the most sensitive for low flow detection. So low velocities may fall below the wall filter settings or be very hard to visualize. So again, if the question says slow flow, deep vessel, weak signal, think power Doppler. So we're almost done with this whole thing, right? So this is like the second to the last question. Let's get started. Just let you know that we are almost done with this set of about 50 questions that we covered. So the question says variance color maps demonstrate a change of hues from blank. And the answers are A, left to right, B, right to left, C, bottom to top, and D, top to bottom. And the correct answer is A, left to right. So variance color maps show a change of hues from left to right across the color bar. So remember that in variance mode, the base color, red or blue, still indicates direction, and brightness still reflects velocity, but the hue shifts horizontally across the color bar to represent turbulence or some variance. So the color progression goes left to right on the color scale, and so that's key. Now let's look at the other answers and determine uh, what's off about those. So B said right to left. So color bars are conventionally displayed with hue progression from left to right. That's just convention, meaning that's just how we decided to display them. And variance is encoded by moving across the bar, so not backward. Answer C says bottom to top. So bottom to top changes represent velocity magnitude, so brightness and intensity, not variance. Variance changes hue horizontally, not vertically. And answer D, kind of the same the thinking there, top to bottom, same issue. Vertical changes represent velocity amplitude, brightness changes, and variance is shown by hue variation across the bar horizontally. So think of the color bar like a rainbow stretched sideways. Velocity correlates to brighter or darker versions of the same color. Variance correlates to color shifts sideways into the green yellow mosaic tones. And that sideways shift is left to right. And oh, that's it. Okay, one more question and we're almost done. And we are at the last question of the last phase of this review in Doppler, the Doppler review for the SPI. All right, so let's talk about this last question. And just a reminder, like you should have already taken a ultrasound physics course. This is just to review and put some concepts together in case that course was a while back for you. So the last question here is, what advantage does spectral analysis have when compared to other Doppler techniques? Spectral analysis blank. And the answers are available are A, is not angle dependent, B, is free of aliasing artifact, C, determines flow direction, or D, displays peak systolic velocities. All right, so I'll give you a second there or two. And the correct answer is D, displays peak systolic velocities. So remember spectral analysis, spectral Doppler. They graph Doppler frequency over time. It shows full range of velocities. It allows you to measure peak systolic velocity, PSV. It allows calculations of indices, so like RI, PI, and S over D ratios. So color Doppler can show direction. It can show general velocity patterns, but it doesn't give precise measurable peak velocity. So what spectral Doppler does is just that. So that's a big advantage. Let's talk about why. Kind of excited to finish this whole review. Let's talk about why the other answers are not the best choices, right? So A says is not angle dependent. Well, all Doppler techniques are angle dependent. So spectral Doppler uses the same formula, right? F sub D is equal to 2 F sub naught, right, times V cosine theta, all divided by C. Or if you're looking at the velocity, if you rearrange that for velocity, velocity is equal to F sub D times C divided by 2 times F sub naught cosine theta. So the angle definitely matters just by the equation alone. And as I repeated before, remember this equation, memorize that equation. Answer B says, is free of aliasing artifact, or no. Pulsed spectral Doppler absolutely can alias. So aliasing is common in high velocities with low pulse repetition frequencies. Continuous wave avoids aliasing, but not spectral pulse width. C says determines flow direction. So color Doppler also determines flow direction. So this is not a unique advantage. Spectral Doppler shows direction above below baseline, if you remember that, but it's not the distinguishing feature. So what it does best, color Doppler shows direction and general flow pattern. Power Doppler shows presence of flow, so it's sensitive to low flow. Spectral Doppler displays measurable velocities, PSV and EDV. And so if the question asks for an advantage, right, measurement of peak systolic velocity is the key in this case. And that is the last question. I want to thank you very much for watching this review over the SPI section, over the Doppler section of the SPI exam. Again, this is just a review. This was not meant to teach you the material. You should have already taken a course on ultrasound, whether ultrasound physics, whether it's a formal course or you were just studying on your own. You should have some understanding of ultrasound physics before doing this review. And this was just a review of the concepts from that course or that self-preparation for the SPI exam. I want to thank you very much for your time and good luck on your exam.